Great, thanks. All right, so I'll transition now to our second speaker. And so this is John Downer from the University of Bristol. John's a senior lecturer in risk and resilience in the School of Sociology, Politics, and International Studies. Broad interests in the nexus between science, risk, and governance. And some of his current research focuses on the risks of complex technological infrastructures, particularly nuclear power, and the technopolitics of the environmental debate, and particularly radiological pollution. So John, thanks for joining us, appreciate it. The question I wanted to tee up for you was that as people talk about a nuclear renaissance or a next generation of advanced nuclear, in many cases, they'll look to other industries, right? Is there a better model for regulation, governance? And there's been discussions about NASA, maybe FDA, maybe aviation. And I thought you could get us thinking about that using the example of aviation, right? And talk a little bit about strategies for public engagement that nuclear should avoid or use, compared to what we might learn from aviation. So I'll turn that over to you.
Yeah, thanks. Thanks for inviting me. I'm happy to be here. I've spent a lot of time sort of thinking about the relationship between civil aviation and civil nuclear. My PhD was about regulation of jetliners, and since then I've done a lot of nuclear stuff with CSAC and stuff like that. And I think they make for a really interesting couple in the sense that they have these kind of unique commonalities, that they're odd technologies in ways that they have in common, right? So both are highly complex socio-technical systems that unusually have to do active work in order to remain safe, right? Because gravity, one's defying gravity, and the other one's sort of containing fission. And partly because of this, both of these systems require what I'm going to refer to as ultra high reliability, right? Which I'm defining fairly narrowly as a sort of mean time to catastrophic failure of 1 billion plus hours of operation. It's difficult to put your finger exactly on what figures they're shooting for, but in that sort of region. Very few things that humans do require this level of reliability, right? This reliability has to be known sort of prior to them being built as a condition of them being built for the most part. We wouldn't build reactors if there was a reasonable chance that they might melt down, right? And the same with jetliners. And so, as a sort of offshoot of this, rising from this, both of these technologies have sort of co-evolved, right? The regulatory structures around both of these systems have sort of co-evolved. So in answer to your question of can we take stuff from the regulation of aviation to speak to the regulation of nuclear? I think the question itself is a little bit, I would push back against the sort of premise of the question a little bit, in that if you look at the structures through which these different technologies are managed, they already look very, very similar. And they've both sort of learned from each other over the years. When nuclear regulation went very quantitative with WASH 1400, and then aviation regulation sort of followed that route. And once you get down to sort of, they end up sort of drawing on kind of common documents at a really sort of deep level of analysis, right? And what both do on some level, the bit that I'm interested in, at least, so managing this sort of ultra high reliability, you've got sort of subdivisions of various regulatory agencies in the US. You've got the NRC and the FAA. They assess and certify the designs of new types of reactors and jetliners, right? And this process is a very, very elaborate process that essentially sort of breaks down to sort of bench tests of individual components and subsystems and then you combine the results of those tests via sort of theoretical models of how the system as a whole works, right, through things like redundancy calculations. And then once you've done that, then the reliability of that system becomes, more bureaucratically at least, becomes a sort of established fact, right? It's no longer questioned, and say nuclear discourse, accidents tend to get written out of any sort of downstream discussion from that, right? So when you assess the economic merits of nuclear energy, you don't cost in accidents because you've sort of proven that they won't happen. And what interests me about this and how I came to be sort of interested in this is through the sort of philosophy of science, right? I was an epistemologist before I was an SDS scholar, sort of philosopher of science, and the philosophers of science are very interested in the limits of proof. How the ways in which the scientific method doesn't quite, you still need to make sort of judgments, right? So all these kind of logical problems, things like, for instance, the problem of relevance, right? This problem that you can never be absolutely sure that your test or your theoretical model perfectly represents the real world in all its complexity, right? Or captures everything that matters, right? Well, to cut a very long story short, to say that you've created a incredibly elaborate technology and you're absolutely certain and confident that it won't fail any more than once in every billion hours of operation is just seen through the lens of this literature is implausible, right? These systems represent vast, unknowably vast numbers of knowledge claims, right? What you're saying is you're absolutely certain of every detail of how metal is going to fatigue or interact with other metals, or exactly how the environment's going to behave, a whole bunch of things, right? You just can't be that certain, right? To say that I'm certain for the next billion hours. A billion hours gives rise to a lot of edge cases, right? It's to say that you've done that. It's like telling a physicist that you've created perpetual motion, right? The epistemologists ought to kind of roll their eyes at this kind of claim. But this is what makes jetliners so interesting, because jetliners demonstrably achieve this sort of level of reliability, right? We built tens of thousands of jetliners, and we operate them 20 plus hours a day, and we accumulate a vast amount of service data, right? So unlike reactors, we can actually statistically say that jetliners are achieve the kinds of reliability that the airframers promise and regulators justify to, right? And so the sort of what I spent a long time sort of looking into is how civil airframers are actually achieving that end, right? How are they circumventing this sort of epistemological problem of how do you prove to achieve these very reliable jetliners? And a very long story short, I'm conscious that I'm probably talking over a little bit. If you look behind the curtain of how aviation regulation actually works, or how reliability in civil aviation works, it doesn't work quite the way, or anything really like the way it is portrayed, bureaucratically, and it relies on things that civil nuclear doesn't really have access to. And so I can expand on this, and I don't want to just speak for a really long time, but I can expand on this in the questions you like. But I think that there's sort of three keys to jetliner reliability. Right? The first is that just that sheer service experience I was just talking to, right? We built tens of thousands of jetliners, and over the last 50, 60, 70 years, they failed in all sorts of ways that nobody predicted, didn't show up in the tests and models, right? And then the second thing I think is what I call a term I borrowed from the SDS literature, a recursive practice, right? And this is this very long-standing commitment that sort of aviation's sort of famous for, of investigating its failures, and figuring out why airplanes fail. They'll dredge oceans to figure out why a jetliner crashed, and they will sort of learn the lessons, and they'll generalize those lessons, and they'll implement changes, right? And the third thing I think is the most interesting part, and probably the most controversial, is what I sometimes call innovative restraint, but I've taken the calling design stability. Right, this is just the fact that we don't change jetliners very much, right? To an astonishing degree, that's massively counterintuitive, right? We've been building it's kind of fair to say that we've been building iterations on the same jetliner for 70 years, right? Since the Boeing 707 in 1958, right? Yeah, and when we do change them, of course, they have evolved a bit incrementally. Everyone points to fly-by-wire and advanced composites and stuff. We change them very, very incrementally. And so any new technology we put into a jetliner, we wait until it's been used in sort of military aircraft for decades sometimes, and then we'll sort of introduce it in ways that are kind of non-safety critical. We'll wait to see how it works out. We'll put sort of the differently redundant systems to sort of cover for them, and it's incredibly cautious relationship to changing jetliners, which has all these benefits, right? This means that we can, every lesson that we learn from these decades of failure, we can kind of revise this, our understanding of jetliners, and it tends to be, we can make our learning cumulative, and we can slowly sort of whittle away at the failure performance of jetliners, right? And it means that these lessons tend to be very generalizable because all jetliners are very, very similar. It means we don't introduce new uncertainties, which is all, essentially to say the airframers, jetliners are reliable, I would argue, because airframers have been slowly refining a common design paradigm for 70 years, right? Leveraging the insights gleaned from hundreds of millions of flights and failures, right? And because of the civil aviation's history with its many disasters was a necessary condition of its modern safety, right? And aviation regulators haven't mastered the art of predicting or policing the reliability of a complex technology to extreme degree of sort of accuracy, as is implied by the 1 in a billion. They're just comfortable with this kind of this common jetliner design paradigm, and have a very good idea from service how often it fails, right? So what does this mean for nuclear? Well, on one level, it implies that if the nuclear industry all committed to a common reactor design paradigm and built tens of thousands of reactors and operated them for decades and suffered through thousands of catastrophes and slowly accumulated the lessons and insights from those catastrophes and used them to refine that paradigm, then probably we could in principle make reactors as reliable as jetliners. But of course this isn't feasible, right? Absent that, nuclear lacks civil aviation's service experience and its commitment to design stability. Well, there's 400 some reactors in the world, and they vary radically. Some very basic principles. You've got molten salt reactors, pressurized water reactors, various generations of reactors that are all very, very different. And so they just didn't have the opportunity to sort of hone reliability in that way. So they actually have to confront this problem in the same way that civil aviation only really pretends to confront it, right? Via sort of abstractions and tests and models with all the kind of epistemological limitations, right? So from my perspective, this comparison that's often made between jetliners and reactors, which crops up a lot, it was someone in the panel yesterday raised it, right? Really tends to be used to say, well, look, we can actually make a system safe, but properly understood, I think the safety of modern jetliners should actually be a reason to be skeptical of modern reactors. And I've way over talked, so I'll stop there. Thank you very much.
Yeah, it's good. Thanks, John. You've got some fodder, I think, for future discussion and stuff. Quick follow up then, maybe. Does it would it behoove with energy infrastructure like a nuclear reactor, you designed it for 40, maybe 60, maybe 80 years, right? So you're not even getting the same turnover that you would with civil aviation. So the opportunity to see the incremental improvements doesn't happen. So is the lesson there that you need to figure out a way to design accelerated aging protocols? I mean, I remember when I was in the Navy, we had a prototype. We trained on it, but it was always designed to stay ahead of the fleet, right? Anticipate the accidents on an example where you weren't actually putting it in the water. Okay? So is maybe there something there to accelerate it aging? Do you see that in other fields?
Yeah, well, I mean, I think there is a difference there in that civil aviation tends to accrue its experience in parallel, whereas reactors actually are around for longer periods of time, which introduces kind of uncertainties for reactors. They have to deal with climate change in a way that civil aviation doesn't. And that gap isn't so wide. I mean, I think the oldest jetliner in service is in its mid-40s at this point, right? So jetliners last a long time. They're not completely dissimilar in this respect.